All right, so if things are going as I planned, we would have in our synchronous meeting stopped at about this point where we looked at the motion of air pressure moving from high to low pressure centers. So some of you are probably familiar with how we measure air pressure. We use a barometer, and for that reason, air pressure is also called barometric pressure. Although we no longer use mercury for obvious reasons. It's easier to use a picture like this to describe how the barometer works. The air pressure is exerted on the liquid mercury. The mercury then moves up the tube, and we measure that on a scale, which is why the scale is called inches of mercury. But we can also measure it in different units. We'll more often use millibars. It's extremely important that you memorize this range of typical values for atmospheric pressure. The lower range, 980, and by lower I mean these are pretty extreme lows that we typically wouldn't see. So for example, if you watch the weather over the course of a couple of months or a year, you're probably not going to see lows and highs near these numbers. These are extreme numbers, but we'll use these just as a general sense to illustrate the range. So 980 would be pretty darn low, and 1050 would be pretty high. So again, numbers that you might not see on too many maps. The reason that that's important is the way that we abbreviate these on weather station models, which we'll be making soon, is that we abbreviate these. And so, for example, if the atmospheric pressure is 989.7, we write that as 897. Okay, so yeah, we've only taken off one number in this scenario, the 9. But our brain has to read 897 as 989.7. All right, so that's why the range up here is important. We know that it can't be 1089.7 because that would be higher than our upper limit listed here. Okay, so it has to be a 9 that goes on here. Second example is 1023.5 is read as 235. Okay, so again, we have to trick our brain into seeing 235 and read that as 1023.5. All right. Again, we know it's not a 923.5 because that would be way lower than our lowest number here. Okay, so for that reason, we can abbreviate these with the last three numbers. All right, and I probably should have put another examples here. If it ends in, let's just say it was 1023.0, then it would be 230. Okay. All right, and the reason you'll see once we start making weather station models is a lot of data that goes in a very small area, and so to make it less confusing and less information in one small area, we take off one or two numbers. All right, so when we think of air pressure, we want to think of the column of air that is above you. We've established that air has mass, and so each of these little particles has mass. And as we move up the air column, there is less air. Right? And so because there's less air as we move up the column, there is less mass. So I like to think about that in terms of this pyramid that we have down here. We've got three people on the bottom, followed by two in the middle, and one on the top. The folks at the bottom, these three, have the pressure exerted on them from the mass of the two rows above them. Right? The person on the top has the least mass exerted on them. There's no one standing on their shoulders. So as we move up the column, there's less mass and therefore less air pressure exerted. And we see that in this column here as well. All right, so as we move up in elevation, the air pressure becomes lower, rising up from sea level. Again, there's less of it up there, less mass, therefore less pressure. And that should be pretty intuitive, right? And so as we watch mountain climbers climb up above the death zone, that point where there's so little air that we need to take oxygen with us if we want to attempt to get to the top, or at least most normal people do. There's so little air, and here you see that as the percent of oxygen. Okay, so oxygen not the only constituent of air, but it gives us a good indication of how little there is mass-wise compared to lower elevations. All right, and so when we look at barometric pressure, we can look at a map like this. If we looked at various locations around the United States in this example, we would be able to record all of the places where there's barometric pressure. Now here the numbers are nice and simple. They're nice whole numbers, no decimals, and a lot of them are the same. Okay, so in reality, it's going to look a lot more confusing than this. But this is a good start for what we're trying to do, is look at a weather map like this and plot the barometric pressure on it. So again, I like this because we can do this very easily. Your students can do this very easily, and it's very easy to sort of follow this. All right, so then we would connect those numbers, and here you can see that those numbers that are the same are connected. So again, very similar to making topographic maps, we're connecting all of the areas that have the same pressure. And instead of that being a contour line, here it's called an isobar. Isobar, barometric pressure, ISO same, isobar. You can see that sometimes there's a circle, just like on locations where there's hills on the topographic map. Very common feature for a lot of these is going to be that we see closed circles around the center of a high or a low. The other thing that we'll see is sometimes the information just goes off the map and there's nothing we can do to connect it. So this 1004 line here, for example, it probably does loop around and make a circle, but we don't have the data up here, so we can't do that. So wherever we run out of data, we just kind of stop that line. All right, so before we get into looking at that, I want to look more broadly at the way that air moves around low and high pressure systems. So to do that, in the investigation manual on page 61 to 65, there's an air motion activity. I really like this activity. The only downside is the directions, while they're clear, can be a little bit hard to follow just because you have to visualize it. So I'm going to try to go through that today. I'm going to try to hold the camera here in a minute and go through it with you. So let me do that. On page 61, the first thing, we're doing two sections. The first is a high pressure system using the map on page 64, and then the second is using the other map, the low pressure map, which is on page 65. So we'll do the high together, and I'll show you what that looks like. So again, the directions are on 61, and it says to find that figure. Ideally, you want to stand up when you're doing this because you're going to model it with your hand, your arm. You've got two bones in your arm, and you can only rotate those so far. You can get a little more rotation out of it if you stand up, so I'm going to go ahead and do that. I'm going to grab this camera and face it down onto the screen, or the map here. So this is the map. Let's see if I can see if this is working. We'll try that. Okay. So what it says is to stand, and it says that you are going to slowly rotate your hand clockwise. You're going to bring your fingertips together and rotate clockwise. So because I'm going to rotate my hand clockwise, the first thing I'm going to do is kind of ratchet back counterclockwise. That way I can turn it clockwise to a greater extent. All right. So I'm going to bring my fingers together around the high, and I'm going to slowly open my hand and move it clockwise, and my palm is going to end up down on the ground over top of the H for high. Okay. Now just imagine that I can dip my fingers in paint, right? And as I do this motion, my fingers are going to leave these trace marks that go around on the map. And that's really what this activity is doing. You're going to number each finger. So your thumb, for example, is always going to be number 1. Your index finger is going to be number 2, and so on and so forth, right? And so I'm going to, probably about 4 times during this rotation, this clockwise rotation, I'm going to stop and write down a number 1 every place that my thumb is, a number 2 every place that my finger is, my pointer finger, and so on until I get something like that. All right. So that's going to be really hard for me to do, holding the camera and doing this with my hand. So I'm not going to do that. But just imagine that my thumb was dipped in paint. You would see this arc that it makes, kind of something like this. It's kind of going to go like this. I don't know if you can see that. So let me put this down. All right. So that's important because the motion that our hand is making, both our palm going up or down, the clockwise or counterclockwise motion, and whether the air is moving in towards the center of the low or out, is all modeled by our hand. Okay, so I'm going to have you maybe pause here and give that a shot before you go on. So the way that that's structured is you'll draw those maps and then you'll answer a series of questions that really have either multiple choice or you can circle an option for this. So let me have you pause there and give that a shot, and then we'll talk about it. Okay, so I think the directions, if you go through them, are, they're there. Hopefully that little illustration that I did help make more sense of that. All right, so if you went through that, you would see that your palm and your fingers for a low came inwards. The air was spiraling, your fingertips were spiraling counterclockwise, and your palm lifted up the table, meaning the air is rising above a low. So we see that over here. For the high, it's exactly the opposite. Our fingers started in the middle. We moved them outwards, so you see the air moving outwards from the high. Our palm went down towards the table, and the direction was clockwise. Okay. So doing that activity, if you can remember two of them, right? If your hand goes clockwise and your palm goes down, then automatically your fingers go out. So you get two of those. The third one comes naturally, and then the high is the exact opposite of the low, and vice versa. All right. So if that works for you, that hand motion, that's fine. Remember that. Otherwise, these three motions are what's important. All right. Upwards above a low, inwards counterclockwise, and the opposite for the high. All right, so if we kind of try to extend those two pictures together, we would see, let me just go back, that if we extend this high around, the air is moving outwards away from the high towards the low and then coming in towards the low. So it's making that motion from high to a low. So we're already established that air moves from a high to a low, and we see that here. This picture is just sort of trying to put that into 3 dimensions. Air rising above the low, sinking down over the high pressure system, and moving from the high towards the low. Another way of looking at that, air coming down towards the high pressure system, moving over to the low, rising. And so this is creating a convection current where warm air is rising, cool air is sinking. And so winds aloft are moving the opposite direction, but we're not that concerned with that. We're concerned with the movement down here at the surface level. All right, so again, another attempt to show all that in an attempt at 3 dimensions. We have the air moving inwards towards the low, counterclockwise, rising, moving aloft towards the high, sinking back down, and moving outwards in a clockwise direction. Okay, so coming back to this map that we looked at before, we've got a map where we can connect all of these numbers. So again, we can make these isobars by connecting all of the numbers that are same, and you'll see that this would make a circle around 1024. That is the center of the high, right? That's the highest number on the map, 1024. There's no number higher than that. So that's the center of the high. The lowest number is a 1008, so that would be our low, and you can see that we would have a circle around the low as well. All right, so if we drew all those together, we've got a bunch of, well, not a bunch, we've got 1, 2, 3, 4, 5 different isobars connected. You can see there's another 16 over here. That's all we can do with that, right? We know it might connect to this, it might not, it's hard to say, we just don't have all of the data. Okay, so we just worry about what we can say, and we've connected that here. All right, again, like topographic maps, pressure gradient, same idea that we have with topographic maps, talking about gradient, where the lines are closer together, there's a steeper pressure gradient. Where they're further apart, there's a less of a pressure gradient. That's important, just like that's a steep hill. In this case, the air is moving faster here. So we look for areas where these pressure gradients are close together, these lines are close together, to see extreme weather happening there. The air is probably moving faster there. All right. So we see that in this picture, just like a topographic map. That's the area of strong pressure gradient. There's probably more significant weather going on there than this region of a weaker pressure gradient. All right, and we see that in a term that you see sometimes, bombogenesis. You see that on the news every once in a while, and that's where there's an extreme drop in low pressure of 24 millibars in 24 hours, so an extreme change. So again, change in air pressure, easy to see, and in this case you can see that that amounts to significant weather. So we'll stop there and pick up looking at fronts and weather.